We now reach the topic of eigenvalues and eigenvectors. The basic object of study is the equation ax equals lambda x. Let's understand the basic components of the equation. A is a square matrix. X is a vector. It has a special name, an eigenvector. And this symbol lambda, that's a scalar. It's got a special name as well. It's called the eigenvalue of the equation. The meaning of this equation is that if you multiply the square matrix A times the vector x, then you get another vector that's pointed in the same direction as x. It's a scaled version of x, scaled either out or back or perhaps flipped around by some amount lambda. In other words, the eigenvector x is in the same direction as ax, and the eigenvalue lambda tells us exactly how the matrix A affects x, meaning how much it scales x. The first and most basic example of this type of equation is when you use an identity matrix. In this example, let's use a 2 by 2 identity matrix. Well, every vector is an eigenvector of the identity matrix, because if you apply that identity matrix to x, it doesn't change anything. So in this case, the equation is ax equals 1 times x. The eigenvalue is just 1 here. That wasn't a particularly interesting example, so let's look at a slightly more complicated example. Now we'll take the 2 by 2 matrix 2, 0, 0, minus 1, and let's see what it does to the vector x1, which is 1, 0, and then the vector x2, which is 0, 1. When you apply a matrix to a standard unit basis vector, it just strips away the corresponding column. So in particular, what we have here is that ax1 is equal to 2x and ax2 is equal to minus x2. So what we would say here is that the first eigenvalue, lambda 1, is 2, and the second eigenvalue, lambda 2, is minus 1, because those are the scalars that show up in this equation. Another thing that we are seeing here is that x1 and x2 are both eigenvectors, and a is being multiplied to each of them, but a affects them differently. In the case of x1, a stretches x by 2, whereas in the case of x2, a flips it around. Let's look at a three-dimensional example now. We have a 3 by 3 matrix A, which is given here, and now let's consider the two vectors minus 3, minus 1, 1, and 1, 0, 0. In the case of 1, 0, 0, we're just looking at the first column of the matrix again. So ax2 is x2. Lambda is just equal to 1. But in the case of the vector minus 3, minus 1, 1, the application of a to this vector actually gives us the 0 vector. So in this case, we see that the eigenvalue is 0. Related to the notion of an eigenvector and an eigenvalue is an eigenspace. So this is going to be a vector space that's related to these objects. So let's observe something. If x1 and x2 are eigenvectors, and both of them have the same eigenvalue lambda, so not like these previous examples where the vectors had different eigenvalues, but suppose you had two that did have the same eigenvalue, then you could add them together and take a of x1 plus x2. That would give you then a of x1 plus a of x2 by linearity, and since each of them is equal to lambda times the eigenvector, you can pull lambda out of the equation. It's equal to lambda of x1 plus x2. Likewise, if you take a scalar and you take a times a scalar times x1, you can put the scalar on the outside of the equation. And so this is then going to give you a scalar times lambda x1, or lambda times scalar x1. So this means that it's closed under vector addition. It's closed under scalar multiplication. Those are the properties you need to be a vector space. And there's a theorem that goes along with this. If you have a square matrix A and a fixed eigenvalue lambda, then the set of vectors for which x is an eigenvector of that eigenvalue, meaning ax equals lambda x without changing lambda, together with the 0 vector, is a vector subspace of Rn. And we call that the eigenspace of lambda.